Good morning, everybody. It's my great pleasure today to introduce our speaker. Our speaker is Dr. Baosen Zhang. Dr. Zhang is currently a postdoctoral researcher at Stanford University, where he works in both the departments of civil and environmental engineering and into the management science and engineering department. Dr. Zhang got his PhD in electrical engineering from University of California, Berkeley, and it's his Bachelor of Art and Science from the University of Toronto in Canada. And he's the proud recipient of a graduate research fellowship from the Canadian government. Dr. Zhang?
Thank you, Daniel, for the introduction. So today I will talk about power systems. As you can see from the title, we'll go from both the physics side and the data side. I will try to see how I can make power systems more intelligent. So we all know that the energy landscape is changing, and I argue there are two fundamental shifts between power systems. The first one is that we're going from a very centralized system to a system that is very spread out. So for example, before we have operators who can control basically everything that's going on in the system. But going in future, that will not be the case. For example, we're projected to have, say, 200 million electric vehicles by 2020. Also, if you look at the picture on the right, this is the famous Nest thermostat that got bought by Google. What this allows you to do is to have sort of smart homes. That is, if you look at these two pictures, now instead of, say, 100 things to control, every household or every electric vehicle could be a point of control, a point you can do active control at. So we're going to a system that could have, say, millions of devices that you have to coordinate and control somehow. This is one shift. The second shift that, as we know, that is going from fossil fuel to renewable resources. And many parts of the US has very ambitious goals to integrate renewable. For example, California has a goal of 30% renewables by 2020. I think Washington State has similar goals, maybe not 30%, but similar goals. And you look at this, this is not a projection. So in California, we do have about 500,000 homes with solar. And this is already starting to create some problems, which our old system cannot handle this anymore. So the story is that so obviously these resources give us tremendous opportunities for a more efficient, greener grid. But it is also a challenge to use them in an integrated manner. And I'll show that it takes sort of tools and ideas from many areas to make this work. So on a higher, more abstract level, we can think of the current system in block diagram level being this, right? We have a power system in the middle, and our goal is to make supply equal to demand. And the knobs we have right now are big generators that we can schedule to make. If we introduce renewables, what we're doing is essentially we're introducing a lot of randomness into the system. So we're making the system harder to control. But in addition of this randomness in the system, we'll also have a lot of new tools that we never had before. We have a lot of new control knobs we can tune to make the system more efficient. For example, one thing is power electronics. So you look at a solar panel or electric vehicle, they all have power electronics that comes with them to convert a DC current to AC current. And these comes for free, and if we use them in an optimal way, we can get a lot of savings, not only combat the randomness, but also get a lot of savings out of them. So this is one thing we never had before. Another new tool we have is demand response. So before, we always saw demand as something fixed, inflexible, and we only change the supply side. But nowadays, with communication or smart homes, we can do demand response. So this gives us another control knobs we can tune in the system. And my first point is that to tune these knobs, to know how we optimally or efficiently tune these knobs, we need to understand the physics of power systems. So it is somewhat surprising that we can get a lot of new insight by looking at the fundamentals of power flow. How does power flow? How does power system behave? This is one part of the talk. A second is that not only do we want to control these new physical devices, we want algorithms and economics all these devices, electric vehicles, solar panels, are owned by individuals. So we need to somehow to manage these. And we need to design algorithm and economics to manage these devices. And the thing that enables us to close the loop here is data. So in particular, we have a lot of smart meter data that we never had before. And this will allow us to design good algorithms and good economics to make the system work. So as you can see from this picture, there's many, many areas to make the power system more intelligent. And today, I'll focus on the demand side. So I'll focus on the side that is closer to the households. I'll show that how everything here comes together for the demand side. So again, from a high-level picture, if we look at the power system now, everything sort of exciting is happening in the transmission side. You have big generators, they go some high voltage network, right? By the time the power flow gets to the demand side, it's a very boring network. We typically have a tree network, and just the power just flows from top to bottom. Not much going on here, so nothing to control. But going forward, as we said, there will be many, many more devices that we can control here. So it becomes a very exciting problem to see, hey, how do we manage all these devices in the demand side? And instead of a sort of top-down power flow, we have two-way power flow. So the first order business is how do we, right? Just to give a scale, as in transmission side, as we said, we may have 10,000 things to manage. In the distribution side, easily could have hundreds of thousands of devices we need to manage on a second-by-second scale. We have to make sure the power is balanced every second. So the first order business is that how do we manage the second-by-second power flow? The second is that if you look at everything here in the demand side, everything is random. In the sense that we don't know how much people will consume tomorrow. So load is random. If you look at solar panels, they're much more random. So the second challenge is that how do we deal with this uncertainty, increased uncertainty in the system? And on a higher level is that how do we organize this? I mean, here everything is owned by individuals. So we need somehow to organize them together, to coordinate them. So if you look at the outline of the talk, this is the outline of the talk, and this is sorted by time scales, basically. At the shortest time scale, seconds level, we'll look at optimizing power flow. And in particular, we'll look at a problem called voltage regulation. So remember we said that California has a lot of solar, and these do cause problem in voltage for the network. There's a lot of voltage problem there. And we'll see how do we use power electronics to manage those voltage, to manage those devices. And another time scale is on the days time scale is managing uncertainty, mitigating uncertainty. And essentially, this turns into a hedging problem. We need to make some decisions today to hedge against the uncertainty or the randomness tomorrow. So this is on the days time scale. And on the years or the longer planning time scale is how do we manage customers. And here we'll talk about problem of optimal selection. So if you look at all three time scales, they're coupled. They're not, right? If we cannot do voltage regulation, or we cannot deal with power flow, I mean, essentially stuff blow up. We cannot deal with uncertainty, we may waste a lot of money. And even if we have the best algorithm, the best physical control, we cannot find the right structure for people to manage people in the system. Nobody will use it. So all these three are very important for us to have a so-called smart grid. And let's talk about the first problem now. Let's talk about the voltage regulation problem. So what do I mean by that? Well, if you look at voltage regulation as, say, you have a power system, take a very simple system. At the left-hand side, you see a feeder. What that means is that's a transformer. You can think that's a transformer coming out the system. And say we have a line network. Typically, if we look at the voltage from the wall outlet, we want it to be nominally 110 volts. Normally, it's not. It drops a little bit as you go down the network, but we'll keep it very close to 110 volts. Now, as we said, we're putting a lot of new devices into the system. let's see what happens when we put in, say, solar panels into the system. Well, if you just put them in without doing anything, the voltage may rise dramatically. And if you let your voltage rise like this, essentially the system will collapse. You cannot operate something here. Electric vehicle give you the same problem. That is, if you just put them in without doing anything to it, just let them draw power, the voltage will fall dramatically. And you cannot sustain this either. So what we want is, we want to keep the voltage at some reference value, say 110 volts. And we also want these new devices to be in the system. So how do we do that? Well, the thing is, the control knobs that we can turn are power electronics. For example, we use power electronics to convert the DC current generated by solar panels to AC currents. And by changing the phase of that, we can inject a lot of reactive power into the system to pop the voltage up, to keep the voltage at a reference value. So this is a pretty urgent problem. For example, in San Diego, they do have a lot of these solar panels, and they do see a lot of voltage fluctuation. So this is a problem we have to solve currently. And the point is that if we can solve this problem, we can get a lot of saving. For example, if we could optimally use the power electronics, remember they come for free. They're already on the devices themselves. We could optimally use those devices just by thermal loss alone. We could save, say, $200 million a year in California. Okay, so the idea is this devices do introduce some challenges, but they also give us a lot of new opportunities to control them. And mathematically, how do we formulate this question? Well, if you look at this voltage regulation problem, we can formulate it as an optimization problem. If you look at the constraints, let's look at operational constraints. These constraints capture the constraints we have in the physical network. For example, we want a flat voltage at 110 volts, so we put it there. We have some reactive power constraints on the devices. We know they can provide some reactive power, but they do have some bounds on them. Also, we have active power constraints. For example, electric vehicle can consume as a range of active powers. We also put them there. And if you look at Kirchhoff and Ohm's laws, those are the physical laws that govern the system. So normally, there are many feasible solutions. There are many ways to do control. So typically, we'll pick the least cost one. And that could be the thermal loss or something else. So if you look at this problem, and if you're familiar with power systems, you'll see, hey, this is the optimal flow problem. That is, this is the basic resource allocation in power systems. And this is a classic problem. This is not new. And since the 60s, people have been talking about this problem. And they also recognize this is a very hard problem to solve. And the difficulty here is that we do have many standard techniques, many tools to solve this in the high voltage network. But at the residential network or the demand side, those techniques break down. But all our exciting sort of new devices are at the demand side. So the question is, how do we solve the OPF or the voltage regulation problem in the demand side? So what are the difficulties? Well, the first difficulty is that this problem is non-convex. So typically, at the transmission level, how we deal with this, we'll say, OK, we'll linearize this. We'll solve the so-called DC power flow problem. But that's not going to work right? Just by the way we build a network, it doesn't work here. So we cannot linearize. The second problem is information connection. Remember we said this is a very large-scale problem with potentially hundreds of thousands of devices we have to control. And they can change from minute to minute timescale. How do we get all this information? Even if we could solve this in a centralized manner, how do we solve it? I mean, how do we get all the information there? So these are the two difficulties we're facing. But somewhat surprisingly, we can make a lot of breakthrough here. So when we look at this problem, and some of our contributions are, first of all, even though this problem is non-convex, I will show there is always an exact convex relaxation. So we can prove a theorem that says you can relax this, make a convex problem, and the relaxation is always tight. So we deal with the first difficulty that this is a non-convex problem. The second contribution is that we get a decentralized algorithm. That is, we do not need to ship all the data to one central location. Instead, we only require neighbor-to-neighbor communication. And we'll go even further than this. We will look at a case where you do not have any communication. So when you cannot communicate and you can only use local strategies, we'll show what you can do there just by doing local control. So these are the three contributions for this. And the idea is, OK, how can we prove such strong result? How do we get such strong result? Well, the intuition is that, remember we said the distribution network was a very boring network. So it had a tree topology for that network. So at the end of the day, we're going to use the tree topology to show how we get those three results. So I just want to give some intuition of the math here. So how do we do that is we'll draw some pictures, and we'll look at the geometry of the injection region. So I promise this is the only slide with a lot of equation 9, and we'll draw some pictures here. So if you look at a two-bus network, remember our system operates as an AC system, so everything is phasors here. So we have a voltage magnitude and angle. And the line parameter is GMB. And at each bus, we're going to inject some active power P and reactive power Q. So this is our simple two-bus system setup. We'll take the voltage to be fixed to be 1. Right? Think of voltage regulation, we want to be fixed at some number. Let's call it 1 per unit here. And the angle difference, theta, is the angle difference between the two buses. So if you look at, with these parameters, if you write down the power flow equations, that is the P and Q of the system, this is active power, sinusoids, basically. And this is the reactive power. Okay? For now, we're gonna focus on the active power. Right? So the problem we try to solve, the optimization problem we try to solve is minimize some function of P1, P2, the increasing function. For example, you can think of this as a loss, which is the thermal loss just P1 plus P2. So if you look at this formulation, this is obviously non-convex. Has sines, cosines, voltages coming in. So normally if people get to this point, they say, OK, it's not convex. Let's do some numerical methods. But we take an approach that let's draw out this region. Let's look at the feasible P1, P2 region we can get. So if we draw this out, right, P1, P2 as a two-dimensional vector is simply a linear transformation of sine cosines. So if you vary the angle from 0 to 360 degrees, you trace out an ellipse, basically, and that's the ellipse. So this is the hollow ellipse. So clearly, this is not a convex region, because there's nothing in the middle. This is a one-dimensional region. There's nothing in the middle. Even though this is convex, this has some very nice properties. For example, suppose I want to minimize some function P1, P2 that is increasing. Can the optimal point be there? The argument is no, it cannot be there. Because this point, the red point, is better in both P1 and P2. So the black point can never be optimal. Remember, we're minimizing increasing function. So we want P1 to be lower. So the red point has a lower P1 and a smaller P2. So it's a better point than black point. Right? That point cannot be optimal. So the only solution that can come out of this, the optimal solutions, lie on this Pareto front. Only lie on this bottom half of the curve. Now let us do a convex relaxation. How do I do a convex relaxation? I take the hollow ellipse, I fill it in. Now I have a convex region, feasible region. Well, you look at this feasible region, and you say, hey, can a point in there be optimal? Again, the story is no, right? Because the Pareto front still dominates that point. There is always a point that's better than the point in the middle. So the only optimal solution lies on the Pareto front. In this case, so the Pareto front of the original of the region is the same as the Pareto front of its convex Hall. So when you take the convex Hall operator and we make the problem convex, you preserve the Pareto front. Since all the optimal solutions must lie on that front, I have a tight convex relaxation. Whenever I solve the problem, I get the same solution because they have the same Pareto front. So this means the convex relaxation is tight. So if you look at this two-bus system, right, when we have the voltage being fixed, we always have a convex problem because the Pareto front doesn't change. So now let's see, remember in our formulation, we have a lot of bounds on active and reactive power. Let's see how these bounds enter the picture. So let's say you have some active power upper bounds, given by that. What that means in this geometric picture is you take those are your upper bounds, you intersect with your region, look at the convex hull, and again you see the Pareto front is preserved. So that means the convex relaxation is still tight here. So we're good. Now if you look at the react power, what happens when we have reactive power upper bound? Remember, this region is for active power. But reactive power is nothing more than a rotation of active power. So these kind of bounds on Q come in as slanted lines, basically, in P. Again, you take the convex hull, the Pareto point doesn't change. So again, we have reactive power working. Now the lower bounds are harder to deal with, but essentially the same story carries through. That is, the Pareto front is always preserved. And that geometrically tells us the convex relaxation is always tight because they always have the same solution. They can only have the same solution. Okay, so the lower bounds, so it take a bit more math to work out, but it still works. So this tells us at least the optimal power flow problem for the two-bus network is not very difficult. We can solve it. Now the theorem is that anything we can do for a two-bus network can be extended to a tree network. Okay, so since distribution networks are mostly trees, this geometric intuition basically carries through. That says for a tree network, the optimal power flow is convex, essentially convex. You can convexify this problem. And so just to contrast the transmission network, OPF is non-convex, and there's an open problem, how do we solve it? For residential networks, since look at the picture on the right, it has a tree structure, so it's still non-convex, but we can get a tight convex relaxation. And the difference is that we have cycles in transmission network. In residential network, we do not have cycles. So that allows us to make the problem convex. So once we know it's a convex problem, we can design algorithms for it. For example, one algorithm we can design is a decentralized algorithm. So take this tree network, for example, the 4-bus tree network. How will the algorithm work? Well, the algorithm works by each node basically will solve its own subproblem, right? The local constraints are the bus power constraints, which each bus knows. Lagrangian multipliers are exchanged between neighbors, and you take that information, and you can solve this problem. For example, you can do this in parallel, 1 exchange with 2, 2 with 1, 3, 4, and so on. You have up these Lagrange multipliers, and you only communicate them. Right? And since we can show the centralized problem is convex, this essentially tells us this decentralized algorithm will converge, and with fairly good rates. Right? So this problem, we're fairly happy with this algorithm. We're pretty proud of this algorithm. So we took it to PG&E. So basically, we said we said that, hey, if we have a communication structure like this, say from neighbor to neighbor, we can solve the OPF in an optimal manner. They said, great. Well, our communication link network is not very good. It's not even that you have random packet drops. It's that link just dies completely. So people think that communication in smart grid is a trivial problem. It's not. It's hard to make this work in practice. So they say, hey, our link dies completely. The second difficulty they have is that we have incomplete network information. Remember, for the decentralized algorithm to work, I have to know the line parameters. I need to know who my neighbors are, basically. I need to exchange some information with them. Normally, utilities often, they don't know that. They say this system was designed long time ago. Something may have changed. We don't have the updated information. So this got us thinking, what if there is no explicit communication? if you look at this system, this is a physical system at the end of the day. So every time, say, if I inject some reactive power here, if I inject some reactive power at the second bus, every bus in the system will feel it. Once I change something at one bus, all the voltage at every other bus will change. So implicitly, you can think of, I can do implicit communication just by changing something, your input at one of the buses. So the question is, with this strategy, how well can we do? How well can we do without any communication? Right, so we call this local control problem. So essentially, so the problem looks like this. So say we still want to maintain the voltage at the flat voltage, at some reference voltage. We're not asking for optimality now. We're not trying to minimize the loss. We just want a feasible solution out of this. So the algorithm is very simple. You sense your local voltage, your own voltage at time t. If it is lower than your reference, inject reactive power. If it is higher than your voltage, withdraw reactive power. So this is a purely local strategy. And equation, so right now equation form is like this. You take the difference and you have some gain there. And our only design parameter is how do we design this gain? We need to design the DIs such that this dynamical, if you look at it, it's a dynamical system. How do we make the dynamical system stable? How can we do that? We need to design the gain such that we have a stable system. And what we can do is we can characterize sort of the necessary sufficient conditions for there to exist stabilizing gains. Now, if you compare the case when we have communication and the case when we do not have communication, we have this. So we want to solve this problem. When we have neighbor-to-neighbor communication, we have the optimal algorithm. When we do not have communication, maybe we can maintain feasibility under some situations, not always. For some parameters with local communication, with local actions, we can maintain feasibility. Now the question is, does power electronics help? If you think about this system, so right now, the local communication can maintain feasibility only under some situation because every bus is essentially a constant power bus. And that is in sort of control. You look at it from the control side, that system is very hard to control. But if we could have new communication, new power electronics, we can change the behavior of the loads. And if we could change the behavior of the loads, we can potentially make the system much easier to control with only local action. So one thing to think for the future is, can we, from system, we look from a system point of view, can we design some new power electronics to help us here? Can we design some new dynamic? Basically, can we sort of induce some dynamics that makes the system easier to control? Right? So going back to our outline, we have solved this. We talked about this problem. Now let us look at the uncertainty in the system. That is, how do we hedge in the system? So you look at these new devices, every one of them is random. Right? Not only that is, you look at solar, you look at sort of nets with smart homes, they'll increase the uncertainty in the system tremendously. And they act on a sort of fast time scale. The problem is that our big generators, our control knobs are big generators. These are slow. Right? To get a coal power plant to generate tomorrow, you need to start ramping it up today. So there is a mismatch in time somehow we'll have to deal with. The question is, how do we deal with this problem in time? So if you look at currently, we approach this problem as this. Today, the system, there is uncertainty in the system. For example, in load. If I predict the load tomorrow, there will be about 2% uncertainty. And what we use is, California uses a 3 sigma rule. That means you look at the forecast load, you look at the error, sigma, let's call it sigma, you buy 3 times that. And that's your, right? So you buy that to hedge against uncertainty. So if we introduce renewables, let's say we have 25% renewables, and say we can predict them very well to about 20% uncertainty. Again, we can do this. We can forecast load minus renewables, forecast this net load. We have larger error now, say 7%. We can still use the 3 sigma rule by that much, right? Now the problem is, before the uncertainty is small. So this costs about $3 million a year for California. If we use the same rule, this will cost about $1 billion for California. So basically, we're wasting a lot of money just putting reserves there. We're not using them. But we're afraid that something will happen tomorrow, so we're wasting money here. So when uncertainty is small, sort of 3 sigma, 2 sigma really doesn't matter. A small number anyway. When uncertainty is big, we really need to be careful. What is the optimal reserve we need in the system? So the one question we want to ask is optimal reserve. The second question is that what really is the intrinsic impact of uncertainty? Suppose I'm doing forecasting, and I go to California. I say, suppose if I can improve the entire forecast by 1%, takes you $100 million a year, is it worth it? Should I pay that money to improve my forecast by 1%? So we want to also characterize what is the intrinsic impact of uncertainty. The way we do that is we'll introduce a so-called market model. So we think about today's market operates like this. We have a day-ahead market. Let's say we have some price there, alpha dollars per megawatt. You do this, you carry this market in day-ahead. At real time, we have another stage with some price being beta. Of course, we'll think it's costs more in the real time. Okay? So we have some demand. Let's say D, we'll decompose like this. D hat is my day-ahead forecast. E is my error. So the problem I want to solve is think of G as how much power you will buy at day-ahead. So this is your day-ahead cost. This is your real-time penalty. So essentially, you're trading off these two. If you buy a lot at day-ahead, you get a small penalty, but you spend too much money at day-ahead. If you don't buy enough, you may get hit with a huge penalty. So normally, when people solve this problem, they took a Monte Carlo approach. That is, you do a lot of samples, a lot of scenarios. That's a very powerful, very robust approach. But the problem is that that does not give us qualitative insights. But we want some we want some sort of deeper understanding here. So the contribution we make is that we'll think of the uncertainty being small sigma. That is, even with 25%. So even when you have 20% solar or wind, uncertainty is only about 7% uncertainty. So this is, in operational terms, this is not very large. So under this assumption, first of all, we'll find the optimal reserve, right? Whether it should be 3 sigma, 2 sigma, 1.5 sigma, we'll find the optimal reserve. The second is that we'll quantify the intrinsic impact of uncertainty. The way we define that is, if you look at the cost of uncertainty, it should be defined like this. One, you have the optimal cost. Suppose you can solve the problem, you have optimal cost. On the other hand, we have a clairvoyant cost. That means, suppose I know the information, I know the realization in the future, what's my minimal cost? And the difference here is the cost of uncertainty or the cost of not knowing the future. And it turns out, under sort of broad conditions, this is linear. So this is linear in terms of sigma. So we have a price uncertainty, which is a number, not dependent on sigma, and right. So this answers us if you can improve sigma by a certain percentage, this is how much we gain by price uncertainty. And if you calculate in California, this is about 500K per megawatt per year for California. So if you could save on uncertainty, this is how much you would save. Right? And all these results extend to the network case. So even when you have a large network, the same result holds. We still have a linear scaling. So the cost of uncertainty still scales linearly with sigma. And just to compare to before, so let's look at our 3 sigma rule that we currently use and the optimal reserve. So let's assume the air is Gaussian. I say there's Gaussian air. And so on the vertical axis is how many sigmas you need to, right? You have to have. On the horizontal axis is beta over alpha. That means beta is the real-time price, alpha is the day-ahead price. That's a ratio. So you see that 3 sigma is a red curve up there. The optimal, we can calculate this in closed form. Q is the Gaussian air Q function. And you take this Q inverse of alpha over beta. So we can see that even when your real-time price is very high compared to day-ahead price, even when you're very, very conservative, still the 3 sigma buys too much reserve. So in practice, this tells you that, hey, a lot of times you hear people talk about, renewables, and we need too many reserves, we need that, is that they're not doing the optimal reserve. So once you do the optimal reserve, it can be a lot more ambitious here. So this is the story here. Okay. So if we go back to our outline, we solve the hedging problem here. Now let us go to the longest time scale, which is managing customers, right? So here on the first part, we said we have a way to control the physical devices. Second part, we said we can deal with uncertainty. The last part tells us who should deal with this. Right? Everybody owns their own electric vehicle. How do you manage them? How can you group them together? Right? So who does the control? Now utilities, currently so PG&E, for example, is this huge utility in California. And they manage everything there. The question is this a good setup? So PG&E is this big because of, right? It's very huge, but is there a correct size? Should it be, is it bigger the better? Is smaller the better? Is somewhere in between the better? Is there a size that utility should be? And if you think back to the last part, it seems that bigger the better, right? Because once I have a very large area, I average all the demand, I average all the randomness, I have a lot of spatial diversity, maybe my uncertainty is low. So it will look like bigger is better. So in this part, I will show not necessarily. Not necessarily. So we can just look at from that point of view. Let's look at the low forecast error. So we're going to look at the hourly forecast day-ahead error. So a single household essentially, well, I say 100% error means you cannot forecast a single household. I don't know how much you will consume tomorrow. It's very hard to forecast. At the substation level, say you take 200,000 households, I can do a very good forecasting job. I can forecast to around 2%. Now the question is, what happens in the middle? How does this scale? And this is really where data comes in. Because before, we cannot answer this question. All the measurement we have is either at some single households, or the utility only measure at the substation level. So we cannot answer the question, what happens in the middle. But nowadays, we have a lot of smart meter data. And that will enable us to answer this question. So the answer is this. So we work closely with PG&E. We took their hourly smart meter data, about 1 million households. We plot the forecast error here. We plot the error there, looks like this. So as the left-hand side is single household, you see huge errors. As the right-hand side, this does scale. So when we go to, say, 100,000 households, this stabilize around 1 or 2%. But the interesting thing to note is that you think everybody is independent. The law of large number tells you that, so this is a log-log plot. This is a log-log plot. So the law of large number tells that slope should be 1/2, and this slope should keep going down. But that's not the case. Turns out pointer doesn't work. Turns out at 1,000 households and 100,000 households, you don't do that much differently. You have the same forecast error, right? So there is a knee here. And let me just make one point. You look at this data, and it seems like we have a lot of data. For everybody who has their hourly consumptions for 3 years, why can we not predict a single household? Why is it so hard to predict a single household? Well, in power systems, the idea is that there is operational meaning to this. That is, I need to predict what happens tomorrow at this specific hour, energy usage. So with all this data, we can predict on average what happens to a single household. We cannot predict specifically tomorrow, say at 12, what will happen. For that, we really need to aggregate some households, right? We need to aggregate some number, but we do not need to aggregate as a 10,000 household level. So if you look at this curve more closely, you see that the first part is basically we have randomness, we're averaging out that randomness. And the right-hand side of the line, we have a systematic error. And it doesn't matter how many people you take, you cannot remove that error. So the first thing we see is that we have huge utilities or huge things managing a lot of people. There's no improvement, really. Not only there's no improvement, there are basically even a loss of efficiency here. That is, there's some bad things start to happen when you go to very large systems. When it goes to very, right? So why is there a loss there? Well, if you look at the aggregate demand curve, say if you look at aggregate demand curve, it looks very smooth. Very easy to, you can forecast this. But the problem is that this aligns with the electricity price. So we have a peak in the afternoon, and the price shoots up. But low in the morning, the price is low. So essentially, everybody here is sharing the same price, right? I'm doing cost sharing, essentially. Everybody shares this. But the question is, not everybody consumes like that. If you look at the people on the left, there's a significant number of people that consumes off-peak. These people only consume before 10, doesn't consume anything in the afternoon. And on the right, those people consume exactly with the price. So essentially, why should the people on the left, do cost sharing with the people on the right? Why should so the people on the left is taking the tab for the people on the right. And there's no reason to do that. Because I can group enough off-peak users. Once I group enough of them, I can do the same forecasting job. I got 10,000 people that's off-peak. I can do the same forecasting job and get a much cheaper rate that way because there's no cost sharing, right? Right, so the question is, how do we group the people? Well, you can think of this price and consumption as 24, they're basically, right? So we want the vector, there are vectors, and we want a small dot product. Right? We want the consumption to be misaligned with the cost. Right? So you take a dot product, that means a small dot product. And here we can calculate the rate for K customers. Suppose say you want to group 2,000 customers, how do you find the best 2,000 customers there? And there's a rate. So the top part is just the price times the demand. The bottom part is the total demand, and this is the rate. Right? So the optimization problem is minimize this rate for 10 K total customers. So this is an integral problem, but there is LP relaxation. So this problem is not very hard to solve if you look at the demand. So once I solve this problem, this essentially gives, right? So I can draw two curves here. The left curve is that the rate will increase as the group size increases. On the other hand, other trade-off is that the uncertainty will decrease. Once I aggregate more and more people, uncertainty goes down. So remember we said the cost uncertainty is proportional, is linear with standard deviation. So we know how standard deviation scales. We have two curves here. And basically, to trade them off, you cross two curves. You got optimal size, essentially. Now that's OK. So what we solve is we have an optimal group for uncertainty rate trade-off. Now the question is this fair? I mean, before, some people had a very low rate. Now we're essentially saying, hey, we only pick the good people. We don't want the bad people. Is this fair? I would argue that this is not as unfair as you think, because this is a more systematic approach than a lot of pricing schemes being put out today. Today, a lot of people say there should be time of use, there should be tier, there should be zonal pricing. There's a systematic way to design it. Also, this may give you more efficient organization. So what do I mean by that is, right? So again, you have these two kinds of groups, have off-peak and peak users. And on the left, I can offer lower rate. Now on the right, I can still offer something. For example, I can offer demand response. Right? If I want to design people to do demand response with me, do not target the off-peak users. Target the people who are on peak. And also frequency regulation. So I can offer different people, different products. So I can be more efficient in my targeting. So today we spend a lot of money installing demand response programs that essentially basically target the wrong people. So once you know their consumption, you can target the right people. So once you can separate them out, you can be more efficient in targeting them. And this basically enables a lot of small-scale, low-therm entities to work. Okay. So more observation about the data is, one question you may have is, well, maybe people they don't consume consistently. Well, typically they consume very consistently. They're off-peak, they're off-peak, they're on-peak, they're on-peak, consistently through the year. So the shapes do not differ significantly by region. Turns out your total consumption correlates strongly with the income. And the reason I show this is because obviously privacy is a big issue here. Once I get all this data, I can have a very good guess, I can guess very accurately. So the question is, we need to deal with privacy here. Right? That's one big problem we need to deal with here. Okay? So we come here, essentially we solve the last problem. So on a higher level point of view, what we design is essentially a layered architecture. First of all, we figure out physically, how do we manage the physical power flows? Have aggregators that manage a bunch of households. And we basically design that how big those aggregators should be, how they have to hedge. And we have a layered architecture. And we have a sort of an optimal way to design this. Now, so before we talk a lot about so for the transmission network, for the high voltage network, a lot of our ideas still carry through. Right? For example, hedging, the uncertainty is also here. We have a lot of wind farms. We can apply the same ideas here. Also, the grouping story still works. When we have a lot of sort of large wind and solar farm, we still need to group them. So a lot of our methods carry over to here. Okay? So future work is that right now, our work with data, we did a lot is, we say, how do we make money, basically, from them? How do we group them? How do we do that? But question is, societally, one ask question is, can we induce behavior change? If I give you all their past data, is there a way to make them behave better? Second is, right, well, data privacy issues. I can learn a lot from the data. We need to somehow hide the irrelevant information there. The utilities tied into that is we saw that big scale utilities maybe need to be restructured to much smaller size. And we saw before that the interplay between power electronics and control is important. Locally, if we can design power electronics, some new power electronics, we can make the control much easier. And again, the wholesale market is a problem because on that market side, we need to deal with randomness, essentially. Okay, just in conclusion, this last slide. So we look at the interplay between fixed and data. We say there are some new algorithms we can design. And I hope I convey that power is a playground for a very diverse range of ideas. We use many tools to design this. And I would say going in the future, this is required. And lastly, let me acknowledge all the people, right? So this is all my co-authors, and that concludes the talk.
Thank you very much, Dr. Zhang. We have time for a couple of questions.
Yes.
Mohammed.
Thank you very much. I think in all your points, there's a lot of work need to be done. So when you say it's this point is finished,
right,
solved, it's not really. There's still a lot of things to be done. But let me offer something. When you were talking about aggregating the errors, of renewable and load forecasting. Actually, in most loads, these two are orthogonal. So it's not just simple addition as you did. So it's actually what they need to compensate for is much less than 7%.
Right. Yes.
Mariam.
I had a question about the first problem, the voltage regulation problem. So recently there has been a lot of work in the literature about conditions under which OFP relaxations are exact.
Right.
How does your work relate to other similar problems? Is it a special case, more general?
Right, so I guess the question is, there are many works showing that when you have, right? I guess our work is the first to offer a proof when it works. So our paper is first to offer a guarantee. Under some conditions, this guarantee to work. That's one paper. The second, then continuing with that, we have the sort of the broadest condition. So we can guarantee basically this will, under all in practice, this will always work. So those are the two contributions. So I guess your question is, so I think Low and Javar, they have this paper, right? I guess you're thinking of that paper. And they have this technique, but they cannot say when it will work. So you can observe in practice, numerically often works. And we're the first one to show you guarantee to work in your tree network.
DJ, one more question.
Right.
Can you say something about how things would change if these are changing?
So the question is, we model as a static problem because there is a separation of time scale. So we think as power electronics is your controller. You can modulate them very quickly. Right? They can converge very quickly. I guess the question is, if things happen on a faster time scale, what happens in dynamics? That's a good question. We're not sure at that point. Yeah.
I think we might have time for one more question if there is one more question.
Okay.
Mohammed, you get a second chance.
Now, more and more of the distribution network are getting to be electric rather than tree structure. How's your algorithm going to avoid that? Because it depends on the tree structure.
Right, so tree structure is one sufficient condition. Turns out we can prove something more general than that. So for example, when you have a cycle with trees hanging off it, this still works, still goes through. So I think a lot more networks maybe have one cycle and a lot of trees on it. So this argument still works. So even when you have a mesh, as long as it's not a very dense network, this still works.
Okay, well, thank you very much, Dr. Zhang.